attending How to Solve a Problem Like Santa Claus by Andrew Francis. Let's give it up for Andrew Francis.
Hi, folks. Thanks for having me here. It's an honor. Just a show of hands, how many of you are familiar with Stackless Python? Oh, okay, so there's a few of you out here. Anyhow, you can tell from the title that Stackless Python, Stackless PY, and join patterns, there's a number of things going on. And during this talk, it may get a little bit technical in the sense that you'll probably end up learning more about how Stackless Python channels work than you want to. But anyway, don't let that eclipse the big picture. The big picture is a lot of this talk is really about experimentation and rapid prototyping. One of the main themes of this is basically either bypassing or speeding up the traditional edit, compile, run, debug cycle by using Python to basically to prototype a feature as opposed to C. But I guess again, the big picture really is to take to have the ability to take a great idea and just run with it. Which leads us to one of the big ideas. A lot, like Stackless Python itself, basically came from Limbo. Basically, these two pieces of code do the same thing. However, they're very different languages. So you have, although Limbo influenced Stackless Python's decision to use synchronous channels, however, they're very different languages. One is basically, statically typed, and the other one's dynamic, and there's many more changes. So there's this issue of influences and interpretations. Also, for me, when I did this talk, there's an element of enchantment. Why do I care about join patterns? There must be something to them that really, really resonates with me. And as I dug into join patterns, I came across this little piece of code. It's from a Microsoft paper called Scalable Join Patterns. And a part of it is this little line here that essentially solves the dining philosophers in one line. Wow. Really, we got to investigate this. And finally, I guess what ties it all together is a challenge. And in this case, the challenge was, I sort of learned about the Santa Claus problem through join patterns. And you see this description, a lot of you, if you've seen beautiful code, you run into this description. I'll tell you what, I'm going to save you the expense of reading that, because that's quite a blurb. But really, the Santa Claus problem goes as follows. I guess it's a cousin of Sleeping Barber. Every year, Santa Claus goes to sleep, waiting for one or two events to occur. One of them is all 9 of his reindeer come back from vacation. When all 9 come back, Santa Claus wakes up, harnesses the reindeer, goes delivers toys because it's Christmas time, and then unharnesses them. The other condition is any group of 3 of his numerous elves come to his door. You see, elves aren't that important, so you need a group of 3 of them. And if a case of group of 3 of them come, Santa Claus will wake up, bring them into his study, consult with them, and lead them on the way. So, you say to yourself, gee whiz, well, what's there to this problem? Well, the reality is, the original solution by Toronto involves semaphores and mutexes. This particular solution is based on one that William Stalling gave. But you see, the perception is, well, there should be a simple queue there. But the reality, you start to get into pretty low-level concurrency features. And the kicker is, when John Toronto first wrote this problem, he got it wrong. It was an assignment for his class, and he got it wrong. And that's sort of over the past almost 20 years, there's been this little the Santa Claus problem has basically become a testing ground for new concurrency constructs. You want to test out how great a concurrency feature in your language is? Well, you try it out on Santa Claus, on the Santa Claus problem. Probably, if most of you have seen the Santa Claus problem, you've probably seen the Haskell solution that uses software transactional memory. That's in the beautiful code book. However, we're going to focus on a different one. we're going to focus on the polyphonic C# one, which is featured, I think the name of the paper is Jingle Bells Solving the Santa Claus Problem in Polyphonic C#. Now, the question is why? The reason I picked that is there's an overlap, or I think there's an overlap between Polyphonic C# and Stackless Python, and that is synchronous channels, and I think they're a pretty honking good concurrency construct. You see little echo, even in C Python, you see little echoes of it if you've seen maybe yield send. The send feature in generators as coroutines. But the essence of a synchronous channel is as follows. You send a message, and if there's two operations, send and receive. You must have a party on the other end for a rendezvous to occur and a message gets exchanged. So in this, you send a message, there's no sender, so you basically block. Eventually, at some time, there's some producer, issues a send, a rendezvous occurs, a message gets passed, and all's good. What's appealing about this is it combines both synchronization and communications, and there's also sort of both parties know that the message got there. Which leads us to Stackless Python. As you may or may not know, Stackless Python is a superset of C Python. If you know of it, it's known for basically having microthreads too cheap to meter. It also sports two modes of multitasking, preemptive and cooperative. The cooperative multitasking is really tied into the messaging system. Also, it can pickle execution state. And here is, I guess, your first full-blown example of Stackless Python, which basically mirrors that diagram that you previously saw. Now, what also makes synchronous channels appealing in Stackless Python is, you could treat them as iterators. This little piece of code comes from the prime numbers sieve. And also, if you notice, a part of being synchronous is you block. When you don't block, you do this little trick. You basically fork, create a new tasklet, and it goes on while you wait. It's a shame I can't show you the entire code for that, because it's quite elegant. Now, we're going to go into a little bit under the hood of how Stackless Python works. And I find the best, because I've been doing these talks on and off for a few years, I realized the best way to do them is actually just use Python structures. And also, this is going to echo it's going to echo about the way we prototype in the future. So basically, this is a chat. I'm going to show you no match. So that corresponds to the first part of that diagram we saw earlier. There's nothing in the channel, and this is the scheduler queue, the runnable list. So we have basically a consumer and a producer there. The consumer is doing a receive. There's no data attached to him, sees nothing in the queue. So after he's taken out, he's put on the channel and blocked, and the producer's next. And you can sort of guess, now there's a match. The producer sees a consumer, takes the consumer off, transfers hello, and puts him on the runnable list. The runnable queue, which is a little detail is it's a round robin scheduler. So far, are folks with me? No, not too complicated. Now we get to join patterns. So this is another example of a join pattern. Okay. Let me. So basically, join patterns are another synchronization and communications mechanism. However, unlike synchronous channels, join patterns support both synchronous and asynchronous mode. These are the rules, but I'm going to explain them here. So basically, what happens is you have your consumer. He's waiting for two variables. He blocks. So these other guys are sending messages, and the pattern's not complete because it's waiting for first and second and wait. So it gets queued up internally. This second guy comes on later. Now the pattern matches, and this guy starts up. But if you notice, these guys don't block like in the synchronous case. They just keep on going on. So the message body in the cord now fires, and it returns a result, and it goes along its merry way. And it turns out to be and those are the cord rules. Another thing to note is you can have more than one join pattern. You can have a plethora of them. I just showed you an example with one. So again, I looked at the polyphonic solution for the Santa Claus problem, and it looked, yeah, I think I could prototype this. So a part of a prototype, because Polyphonic C# is a different language, very different language from Stackless Python. And also, I'm going to build up on something I did in the past, so I make a bunch of assumptions. Some of them are simple. I'm assuming that my senders don't have to be asynchronous. They could be synchronous, and if I want asynchrony, I can mimic it. I assume that the wait here is basically the equivalent of a receive in Stackless Python. That simplifies implementation. And also, message bodies, I don't know about them. I have a sneaking suspicion that they're there because Polyphonic C# really doesn't have channels in the same sense that Stackless Python has channels. But that may be a bad assumption. But still, I'm going by a little rule that I remember reading in a book called, in a paper called Hints for System Software Design by Butler Lamson. When in doubt, leave it out. So we'll see if this actually works. So now and also there's other little things with the prototype, because it is a prototype, so I don't try to make it perfect. I just want to test to see if the concept works. So now we're going to move to Stackless PY. As you can guess, Stackless PY is written in Python. Matter of fact, it's how PyPy implements Stackless Python. More exactly, it implements a large subset of it. However, the interesting thing about Stackless PY is it's really, until very recently, even if you looked at the code, it's essentially independent of the lower level concurrency. It depends on a lower level concurrency package. So for a while, it supported the coroutine package that came with PyPy, but also supported greenlets. So you could do something really, really neat. You didn't need PyPy. All you did was you took greenlets, installed it, took Stackless PY, installed it in lib, and away you go. You could actually run a subset of Stackless Python programs in CPython. However, you use this trick for prototyping. It's great for prototyping, so you get a very quick loop. And that's what we're doing. And a few years ago, I tested this idea out by implementing a feature called select. What select does is it allows a tasklet to block on multiple channels, and it will wake up when there's a result on one of them. For various reasons, this feature isn't in Stackless Python, but it's in all the Bell Lab languages, like Go, Limbo, Newsqueak. So basically, that's when I prototype this feature, that's what its signature looks like. You see, there's a bit of a problem in the sense that in Stackless Python, everything is implemented as objects in a library. However, in the Bell languages, they're language features. So you have to somehow get around that. So these chanops, like this is what you saw before, that's what they look like. And hence why I use words like case, because I'm thinking about this in mind. Okay, the title of this is wrong. Here's the one last big thing is in Stack there. Okay, this is basically the interface for the scheduler. In Stack, this is something that actually not shocked me, but it took me aback a little bit when I thought about it. Because I would look at Stackless Python code, the C-based code, and I look at Stackless PY, and I would notice that there's changes in the implementation. That, in the C-based Stackless Python, the runnable list is a linked list. However, it's a deck in Stackless PY. And this, again, has implications. The code is simpler. Also, when we implemented select, we implemented it we prototyped it first in Stackless PY, with Stackless PY, and then we wrote a C version. And I think the difference was the Stackless PY version of select was about 150 lines of Python, and the C version was about 1,000. So you can start to see the power of using Stackless PY to prototype a feature. Okay. So let's move on a bit more. Now things are going to get a little bit stranger. When I went about implementing select, I read a few papers. Luckily, there are a few papers out there one paper out there that's really, really good. The implementation of newsqueak. It basically, you could write a clean room version of select from it. By a very clear paper written by Rob Pike. However, I did something strange. I posted in the Go mailing list. And I said, hey, I'm a Stackless Python developer. I know that Go and Stackless Python share a common ancestor. I want to implement, this feature. And they basically said, oh, okay, well, and I asked a few questions. And one thing they basically said was, well, Andrew, why don't you just take a look at the Plan 9 channel code? So me and a friend, we looked at it. And it's not in the paper, it's not in the Pike paper, but in the code. It has this really powerful abstraction. It turns out that you think that select is a special case, but really it turns out that these things like channel receive, channel send are special cases. Everything is implemented with the select algorithm. There is just one algorithm to rule them all, and it's really, really elegant. But you have to look at the code, you have to look at the channel code to see this. And this is the actual implementation of the algorithm. I'm going to go through it really quickly. Basically, what it does is it takes a bunch of these chanops, it checks if they're ready, and it randomly selects one. If there's more than one ready, it will randomly select one and execute it. That means that you have a match. Otherwise, what it does is it queues up everything and takes the coroutine that's running off the runnable list. Sometime in the future, this is another guy doing this action will put the block code back on. So you'll find out who the operation is, and you just return it. It's a very simple, very elegant algorithm. I don't know why that's not in the practice of programming. So the trick that I do with join patterns, okay, the one other thing I should state about select. Select is essentially an OR. you're taking this operation or that operation. It's about or. Join patterns, on the other hand, are about and. The trick that I pull is this. I treat a join pattern like it's a channel. They share the same interface. Internally, they're just a conjunction of chanops, of these operations. Do people follow that? So now you have something really nice. This algorithm doesn't even have to change. You just plunk it in and it will work. Polymorphism is your friend. However, in order to get all this to work, you have to add additional rules. Before, with simple synchronous channels, there's only one rule: match. There's only one rule. However, for this, you have to add some new rules. The first rule, I sort of, after one or two failed prototypes, I finally figured out that you need this rule. Basically, what it says is this, and I'll get a bit more into what's inside. Well, you've already sort of know what's inside join patterns, but sort of like, because you're waiting for multiple operations to succeed, whenever one occurs, normally you'd have a match and the guy, people would be scheduled. But what you do is say, I know you've matched, but I'm still going to keep you on a queue, but I'm going to put a little marker on you to tell the system that you're a part of a join pattern. So in this case, yes, the other little thing, because I didn't go into the algorithm at detail, but here's another thing you may notice. The structure of the channel is radically different from the Stackless Python version. In order to fully support select, the internal structure gets far more complicated. You have a receive queue and you have a send queue. So what this little piece of code basically says is, well, Santa's waiting on there's a Rudolph channel. And Santa's waiting for Rudolph to send him data. And Rudolph does. However, what the system says, well, Rudolph, this is a part of a send pattern, so I'm not going to, instead of a rendezvous occurring, I'm going to put you on the send queue and block you. And I'm going to increase my pattern count. So that way you get everything, hopefully you get everything queuing up nicely. So you don't have this clutter. Your clutter for lack of a better word, your user space. Here's another one that I got from, it's mentioned in one of the papers, modern concurrency abstractions, stealing. And this is going to lead into a very important concept. So Rudolph's waiting, and he's a part of a joint pattern, but Mrs. Claus, for whatever reason, needs Rudolph. And so what I do is, I say, okay, you've matched. So I take you off, and I lower your count by 1. Actually, I do one more thing. I have to put, there's a slight mistake here. I put a Santa receive back on there. Okay, I have to correct that. But it's a reversing, so you steal. And it leads to a very, very big concept. Remember earlier I showed you the dining philosophers, the dining philosopher one-liner. There's one thing I think I forgot to mention. With join patterns, there's a very important concept that when there's a match, all the data is transferred simultaneously. It's all or nothing. But there's another notion in the implementations which I try to adopt, is you don't hold and wait for resources. You mark them, but you never own them until you actually own them. You have maybe a lien on them, but you don't own them. And this leads to it basically, what I think, this is my pet theory, that I think it basically, it's sort of like, it served protection against something they call in deadlock hold and wait. And dining philosophers it's traditionally an example of holding and literally holding a chopstick and waiting for another. So that's why I think that thing solves it in about one line, but I'm not quite sure. Oh, geez, there's a little bug in this. What happened to Prancer? Anyway, so I'll say this. I don't really adhere all that much to PEP 8, so please forgive me. So basically, this is my first. Although, actually, also what's a bit of a shame is I should have showed you some of the examples of doing the Santa Claus problems with mutexes. They would fill up several pages. Although, if you want to see the essence of the William Stalling one, which I showed earlier, there's a really great book called The Little Book of Semaphores by, I think it's Dooney, and he shows little hints of how it's done. And it's written in Python using, I guess, the pthread library. Since I don't do things that way, I really don't know. But anyway, I'll tell you how this was my first attempt at it. Where I have basically, this is really select under the hood, but I'm pulling the same trick that I did earlier when I show you that a channel receive is really a select with one operation. I sort of do the same thing, because I also wanted to experiment to get that. If you, again, look at the dining philosophers, you have this telescoping style where you say join when and initially I wanted to do it like that. So this will solve the Santa Claus problem. It more or less looks, it's very short. However, this solution is not there's problems in it. And it's around here. I'm basically exposing what's really internal methods. I shouldn't be exposing ready. And also, if the non-preemptive multitasking system sort of helps us, but really, if we had a different system, you could get a race condition under this. Because a really big concept is things like this, the underlying select is not based on the channel being ready, it's based on it being complete. This is more like a Unix select way of doing things, and that's bad. Back to, now again, the reason I say this is a sketch is because I haven't tested it yet, and I haven't had half an hour to change the code to support this. And also, I sort of like this because it's more minimalist. I'll give you a little story behind this. About 2 weeks ago, I was sort of a bit naughty. Some guy, again in the Golang nuts mailing list, said, well, what's hard to do in Go but easy in some other language? It's a dare. And I said, well, why don't you try the Santa Claus problem? And there's this one guy there who, Roger Pepe, I think he's from Bell Labs, and he writes a solution. He says, I don't think this is all that hard. So he writes a solution. And I look at it, and I realize he's made one mistake. He didn't get the priority right. And then I started talking to him, and then he says, well, I noticed that I made another mistake. I don't let just 3 elves in, I let more in. However, the essence of his solution's really, really nice. He uses select twice. And that nicely handles the priority problem. And I also noticed that when I implemented select, I forgot default, the default case. So this one works really nice. Again, and rather than using a join, I exposed the select, and these are patterns. A pattern returns, if it's elves, we have to check if there's reindeer ready. So we check the reindeer against the default. If it's reindeer, okay, the pattern we want is reindeer. So if it's reindeer, we do all this, else I should put elves. Again, that's why I say it's a sketch. I haven't actually run it. but I'm almost sure it will work. What else did I want to say about this? Yeah. What's interesting is, when I run this, I would say maybe once every like 500 or so iterations, I will get a case of both reindeer and elves show up at Santa's door. So it doesn't happen often, but it does happen. And just checking the priority makes it difficult. I could actually do other tricks. You see, there's other languages that have implemented join patterns. I think in Join Java, they allow you to have order. But I don't want to really put order or priority, because then I think I'm jury-rigging my solution. And I just want a general one. So anyway, in conclusion, yeah, it's possible to do a limited form of join patterns. I've done it. I've done it for Santa Claus, and I've actually done it for dining philosophers. However, there's problems. One of them is, I think the API is very complex. It's complex. I haven't figured out how to get it simpler. And also the machinery is a lot more. So I really can't like if I wanted to move from the prototype to Stackless Python itself, people would just turn around and say, well, Andrew, like, what are the use cases for this? The API is terrible. It may be this nice little academic idea, but it doesn't really solve anything. You're not solving anyone's problems. And also, Stackless API has been relatively stable for, 5 or 6 years. So it's a nice intellectual exercise. Anyway, but all that may be irrelevant. Because right now, the idea that I showed you in the beginning is you prototype, and if you think you got a nice feature, you go through that whole cycle again, but with C. But with PyPy, because what's happening is they're starting to integrate the JIT with continuates. And also there's STM. So that may be irrelevant. It may be just simply a case, you write what you want in Stackless PY and let PyPy do the rest. And that's a really, really nice future. Anyway, thank you.